one of the challenges, I guess, with dealing with vendor models is quality and accuracy. And this comes up. I saw you just roll your eyes a little bit.
Oh yeah.
I think this comes up way more often in the context of like IBIS models, or possibly like touchstone files. Maybe if you're getting something from like a connector vendor or something. But I don't think I've ever heard of anyone bring this up in terms of models for the IP that is going to go onto the die for, like, example, a DDR4 PHY.
Yeah, you hit a soft spot, right? This is something very close, near and dear to my heart, right? This is why I created my LLC, just so I can address this gap, why I love working with Steve and Heidi, because this is such a problem. Even at where I work currently, we have our own measurement-based model library that we created because there's such a gap in vendor models today.
Hello, everyone, and welcome to the Altium On Track podcast. I'm your host, Zach Peterson. Today, we're talking with Ben Dannon, who works at a major aerospace and defense contractor. He is also going to be speaking at EDICon in October, and I thought it would be a great time to have him on to see what he's going to be speaking about and learn more about what he does for work. Ben, thanks so much for joining us.
Hey, Zach, thanks for having me. It's a pleasure to be here.
So you have been brought up many times in my conversations with Heidi Barnes and Steven Sandler, and I know you've done some work with them. Also, if people follow you on LinkedIn, they probably know that you're a familiar face on or on conferences like DesignCon. So maybe you can tell us what it is you do and how you got involved in the electronics industry and what you'll be speaking about at EDICon this year.
Yeah, so okay, there's a lot to cover there. So yeah,
Yeah.
Heidi and Steve, we call ourselves the Three Musketeers. I'm very grateful just to get to work with them. Started working with them back in the early 2020 2021 timeframe actually. And so we've done a bunch
I
of EDI
noticed that.
cons. Yeah, a bunch of papers now. We're doing another paper this year at DesignCon. For the paper at DesignCon this year, it's with Steve Sandler, Heidi Barnes, Aiden Ezra from Broadcom, and Yuniv from Monolithic Power. And so that one is about designing a 2000 amp power supply and the challenges. And Steve Sandler at Picotest is making a 2000 amp step load just to test this power supply. So that alone is a whole challenge in itself. So that should get your mouth watering just thinking about how are you going to build or even make something. I mean, there's water cooling, refrigerating, all sorts of things that he's doing just to make this thing. And so, yeah, I'm just grateful to get to work with them. The EDI Con topic, that is a paper that I'm doing with a good colleague, and a great colleague actually, and a friend, Jim Kashevsky. He works at the same aerospace and defense contractor that I also work for. And the name of the EDI Con paper is What is Enough? BDDQ Power Integrity Analysis with a DDR4 PHY. And that is going to be a ton of fun. It's on October 4th, and we are going to be presenting some of the challenges and a bit of a story that we kind of wanted to share with folks on what do you need to consider when you're integrating a DDR5 with your package from another vendor? Because in actuality, most people aren't going to design their own DDR4 PHY. They're going to buy it and license it from a Cadence or a Synopsys or somebody else, right? And so when you integrate these die models and you get these die models, you want to do the power integrity analysis. You already have enough to worry about when it comes to doing end-to-end simulation and doing sign off of your package, let alone worrying about if the die model is correct. And so the whole premise that we are presenting is, well, what happens if your die model is not correct? What do you do? I mean, your voltage margins are already getting smaller, and so you have to manage that. And how do you know if it's not correct? What are considerations? So it's going to be a ton of fun. That's just a bit of a teaser and kind of what we're going to talk about. We can go into more of that if you'd like. And then on the electronic side, yeah, I have my own LLC. I have it, Signal Edge Solutions, and the whole premise is to do measurement-based modeling, simulation, and EM. So I do it so I can play with folks like Steve and Heidi and others and grow and have fun. Because this industry, um, I love signal integrity and power integrity. It's a passion of mine. And I've been doing this for a number of years. Started my career off at another defense contractor. Then I went to Bosch. Then I went to a robotics company, and now I am where I am, and I have my own LLC. And so along the way, I was in the military and served in a bunch of things, and really kind of found my niche in the modeling and simulation space. So ultimately, I'm just having a ton of fun and just happy to be able to play and work with these other folks, learn and grow. Yeah. So it was a lot. Hopefully I covered everything, right?
Yeah, I feel you on the having fun part, and I know with my background, it kind of made me naturally gravitate towards simulation and analysis, more so than just pure design. So I definitely understand where you're coming from. You brought up with regards to your EDICon talk, you brought up the use of IP in some of these components for like a DDR5. I think for most of our audience, they may not be aware of how this all works. And so, really, what you're looking at is not just the PCB and not just the PCB plus the package, but it's really from the bump all the way down to the board. And that's where we
Hmm.
have to consider power integrity rather than just stopping at the PCB and then whatever the input is on the package.
Yep. Yep. And that's really actually a challenge, right? Because when you integrate this IP, right? Let's just say you work at a company designing a custom ASIC, like what I'm doing here. You might have pieces of that ASIC that is your design, your proprietary technology, but your team is only big enough, so you're going to integrate IP from other vendors or license it to kind of meet those in functionality, requirements, performance, and where you want to integrate that ASIC to perform, right? So maybe you need more memory, so you're going to buy an ASIC DDR4 from somebody else and integrate that on your grid, right? And your point is very valid, right? Most of these IP vendors, these ASIC designers that are making these these pieces of IP, they're speccing the compliance point from a voltage perspective to the die bumps. Exactly what you said. So if you're designing a substrate or a package, you need to understand how to model it to the die bumps and check compliance at that point. And in this case, that's exactly what we're showing. And these ASIC designers and IP vendors can give very complex sort of requirements where in this instance in the EDICon paper, they gave us two specs for the DDR4 PHY at the die bumps. One was we had an overall ripple spec that was less than our clock, right? In this case, if it's say a DDR4 2400, our clock is 1.2 gigahertz, right? And then we had a different, tighter, smaller AC spec greater than our clock. And so that's not really intuitive for most designers from a power integrity perspective, but you have to know how to filter that and then present that. And that's what I show you in the EDICon paper, right? So you can check for compliance.
I see. Okay. So the one of the challenges, I guess, with dealing with vendor models is quality and accuracy. And this comes up. I saw you just roll your eyes a little bit.
Oh yeah.
I think this comes up way more often in the context of like IBIS models, or possibly like touchstone files. Maybe if you're getting something from like a connector vendor or something. But I don't think I've ever heard of anyone bring this up in terms of models for the IP that is going to go onto the die for, like, example, a DDR4 PHY.
Yeah, you hit a soft spot, right? This is something very close, near and dear to my heart, right? This is why I created my LLC, just so I can address this gap. Why I love working with Steve and Heidi, because this is such a problem. Even at where I work currently, we have our own measurement-based model library that we created because there's such a gap in vendor models today, and it's not just us, right? Go ahead.
Well, and you're right, it's not just you, but I see this come up pretty often on, like, SI lists.
Yes. Yes. I mean, I can tell you for a fact the IBMs, the Intels, the AMDs of the world, they all have their own internal measurement-based model library because there is no standard for things like capacitors and passive models. And so Murata just gives you these models for free, but there's no standard that says how they measured it and whether or not that additional path inductance is part of that model or not. For IBIS models, the standard is great, but the challenge is as integrators or designers, it's our job to hold these vendors accountable. And what the IBIS forum teaches you or teaches folks that are paying attention is ask for a quality report. They actually have whole presentations on the IBIS forum that says, what is a quality report? What is an IBIS quality report? Ask for it because there's a checklist. Most people may not even know. Did you know that there's an IBIS quality checklist? So when you get an
I
IBIS
didn't know that.
model, yeah, there's actually a checklist, and IBIS Forum is actually trying to teach and promote this, like saying, hey, you got an IBIS model, asked for the IBIS quality report, which shows they went through and checked all these different pieces of that model before they just released it to the wild. And that's important because how do you know that IBIS model is good, right? What did they do? What did they check it against? How did they build it? And these are simple things that can help prevent errors and mitigate any sort of human factor that comes into play. And that's what happened with this EDICON paper, right? I mean, there was no quality check. I'm not saying there's a standard, but that's one of the things I asked for, a simple method when it comes to any sort of dye model, right? Because when we talk about dye models, there's two pieces. There is the passive portion, which represents your C dye and R dye, and R dye is just the resistance to the grid, right? And you can extract that with dye modeling tools. Both of those you can extract. Then there is the active portion, which can be represented a couple different ways. You can represent that with a piecewise linear waveform, a PWL waveform. You can use an IBIS model, right, that's attached to your passive dye model, right, that's generating those currents. And there's a couple other techniques, but those are the two biggest, most common. And so when I got this passive dye model, I looked at the value of C dye and I said, for a memory controller, there's no way this is right. Absolutely no way. I went back to the IP vendor and I said, hey, do you guys know your C dye value is really quite low? It was 3.29 nanofarads. And I said, that's really low for a C dye for a memory controller. And this is a BY 72 memory controller, right? So it has to drive 72 DQ nets plus all the strobe, plus all the CAC nets, etc. And they're like, yeah, that's right. I'm like, can you just do like a back of the napkin calculation? Very simple, right? We know C equals epsilon A over D. You can calculate the value of capacitance for any MIM caps or IDC caps on your PHY and multiply that by the total number. And you usually find that what you extract and that number, what I call the back of the napkin calculation, match. I've done this many times, right? And they're like, yeah, no, it's right. So I never got there. I'm like, oh man, they're going to make me really go through and show them this number is wrong. So then I went and I grabbed, and I talk about this specifically in the paper, I went and grabbed a Micron SDRAM model, right? And I pulled up the IBIS quality report, and then I even plotted, because they give you the dye models, right, with their IBIS models, so you can do this sort of analysis. Micron does a great job of this. And so I plotted the C dye, and I showed the screenshot of the IBIS quality report, and it shows double the C dye for an SDRAM, for a BY 16 SDRAM, right? So it's only driving 16 DQ plus strobe, etc. And it's double a BY 72 memory controller. And I said, are you guys sure this is still right? You're still telling me this is right? Like, yeah, that's right. I'm like, okay, so you're going to make me go a step further. All right, so then I built the engine.
Sorry, real quick. You just would have reasonably expected that it would have been 4.5 times larger, right? The C die on this PHY.
Typically, I expect something anywhere from 4 to 5 times larger than that. Yeah, okay. With my experience with memory controllers, like you can grab a good example, a Versal, the new Xilinx or AMD ACAP, right? They call it ACAP, but I still, in old school, and call it an FPGA. That has a hard DDR4 PHY on there. I've looked at that C die many times. I think it's like 15 nanofarads. It's in that ballpark, right? So already, an order of magnitude greater than what I had. And so for a memory controller, just knowing what it's doing, right, versus a DRAM, something just didn't pass the smell check.
Yeah, for sure.
Right. And so I showed this to the IP vendor, and they're like, yeah, it's right. And I'm like, okay, I'm clearly not talking to the right people. And it's like any, billion-dollar company where they're all big, we're all big. And so it's, you just got to break down the right barriers. So finally I built an NM model. Our schedule's now slipping. And I showed, look, we're not passing the spec. In fact, you can see I have perfect transmission lines, which loading, right, the die and everything. And everything's perfect and matched. There's nowhere passing the spec. In fact, we were violating their spec by 2 times, right? Twice. We were more than double their spec.
And right, like, so double the ripple.
Exactly.
Yeah.
And so that's the whole premise of this paper, right? And at the end of the day, I show a calculation, how to calculate what the minimum C die needs to be using their worst case transient current from this model. And what you find, or what I found, which makes sense, right? It goes back to this basic physics, things that folks like Eric Bogatin and Larry Smith teach in one of their books that show how to calculate what the minimum CDI is based on the worst case transient current. And actually, I referenced their book in this paper, and I show that. And what I calculated is around 6.2 nanofarads. The IP vendor came back and said, yeah, the CDI is actually 6.49 nanofarads.
Big
Oh,
surprise.
go figure, right? Exactly. So as soon as I put that in there, what do you know? We're passing spec. So it's a really fun story, but these things are not intuitive to a lot of folks, and you have to really pick at the details. And to be honest, building a DDR end-to-end model like this is not easy. I used Keysight ADS to do it, and I use it for many reasons, but already it's complex enough. Not only do I have a memory controller, but I have 9 DRAM. I have their die models. I have the die model for the DDR4 PHY. I have transmission lines loading all the DQ, CAC, strobe, clock nets, right? So I have that current correct. You have to have ODT. It's a very complex model just to build to get it right, and it takes time. And so that's the whole premise here, right? How do you do it? How do you know? And how do you work through the process of understanding what to pick at? And so that's what we did. So I'm really excited to share the story. It's going to be a lot of fun. Yeah.
It's really a guide to complaining to your IP vendor then.
Yeah, I mean, the takeaway is ask for a quality report, ask for something, right? That's the takeaway at the end is if you're getting these models from these vendors, right? I always teach my mentees trust and verify, right? Don't just blatantly take that and put that in your simulation. I mean, it goes back to Eric Bogatin, right? Rule number 9, what do you expect to see? And it's like, well, if it's not passing, I expect it to be passing, you got to be asking yourself why, because they gave us this model and it should be passing under the worst case condition. And if it's not, it's unlikely they designed their PHY incorrectly. That'd be a pretty bad thing.
Well, on top of that, I think you look at the company that is providing the IP and the model, and you probably say, "Hey, these guys have big budgets. They hire smart people. Um, they can't possibly be making a mistake, right?" It's easy just on its face to look at who's coming from that position or who's giving you that model, and saying they know what they're doing. We must be doing something wrong.
That's the challenge, right? When you integrate IP from other vendors, or even if you work internally with your own ASIC team, the amount of files for a PHY, let alone an entire ASIC, it's gigabytes and gigabytes of data. Like the deliveries you get, it's so easy for these things to get lost. And the problem is by the time you're ready to look at that data, because you're at that part in your design cycle, sometimes it's too late. And teams are only so big, and it's hard to vet all the data that you're getting from these vendors to make sure it's right. And so what ends up happening is these IP vendors, Cadence, Synopsys, doesn't matter, right? They're just compiling based on some contract that you have to license this IP, and they're just giving it to you through some sort of secure drop. And it's hard to parse through all that all at once and know if this is right, unless your team is big enough, and nobody's team is always big enough to go through that. And that's another challenge in itself. And that's where some of these kind of gaps come in, which is why I teach ask for some sort of quality report, so that way you can at least help force them to do their due diligence up front. It's not perfect, but it's a path forward, I think, in the right direction.
Now, here's a hypothetical. Suppose that you didn't notice this, and you said, "I need to throw whatever I can at the wall and see what sticks, and get to a design that works within, or at least as close as possible to spec." How would you do that? Because I bring that up because it seems that it's going to force you to get way over conservative
Yeah.
when you have that kind of an incorrect model.
Yeah, that's a good question. And so I actually talk about that in the EDICon paper also, just to prove the point on how important getting that die model correct is, right? And first, we go big to small and talk about, okay, what is a die model? And then we go through what does a die model look like with the package? And we all know, and if you don't know this, but we talk about this Bandini mountain, right? Which is really that cue point that occurs between the package and the die model, and it's a function of the inductance between the package and the die. And so I show a simple case study where we put say 8 microfarads, excuse me, of on-package caps, and we have 1 nanofarad of C dye, and I hit it with a step load. And you can see I have something like 130 millivolts of ripple, which is quite high. And then what I do is I show the same step load, but instead of 1 nanofarad of, I'm sorry, instead of 8 microfarads of on-package capacitance, I go up to something egregious just to prove a point. I go up to 100 millifarads, right? You would never, ever design a package that way. In fact, the packaging team would shoot me and say, "You're crazy. You shouldn't be in the packaging business if you're if you're asking for this." And so, reasonably, 8 microfarads is reasonable for a package for, say, a DDR4-5 power domain, and that's why I'm showing this example. But the point is that with that step load and that egregious amount of on-package capacitance, the peak-to-peak ripple at the die didn't really change. It changed by like a fraction of a millivolt. Instead of like 130, it was like 129 or something. It's in the slides. It didn't change very much. And the point is that the inductance between the package and the die is dominating. And this is showing the importance of having the right die model. And then in the next instance, I just went back to that 8 microfarad on package capacitance and just increased C die by 5 times to 5 nanofarads. And you can see a 50% improvement in the response, and then go to C die at 10 nanofarads with 8 microfarads of on-package caps, and it's another 30% improvement. And so this is just proving the point, right, to designers what you can do and what you can't do. And the takeaway is that C die is really important to make sure it's right, because not only does it impact your ripple, but it impacts your jitter. Okay, but there's only a limit on how much on-package capacitance you can put on there. There's a point where then no matter what, if you have the perfect package in the world, you're always going to have inductance there, and you're going to be fighting that. And it doesn't matter what you do. You can't get past a certain amount of inductance. And so to your point, to your question, what can you do? There's nothing at a certain point, right? If you don't have the right amount of on-die capacitance, there's nothing you can do. And this is a known thing, right? And this is where everything kind of lags the ASIC, right? And when it comes to packaging design, this is where you really need to make sure the ASIC, and the ASIC designers usually are really good about doing this, are putting the right amount of C die on there, right? The right amount of mem caps. Occasionally that gets missed, and the package might be able to pick up some of the slack, but it's limited. It's very finite. Most of the time, it can lead to another tape out on the ASIC to fix that.
Well, that brings up another question here, right? Because when you see in the documentation that they give you that C die is really low, I think the next thing that you think of is, well, okay, if they're saying the model is correct, did they really just put that low of capacitance on there? And why, if
No.
they did, and I need to have, I need to have, like I would, like you said, 4 or 5 times as much, should I even be using this vendor?
Well, those are two very different loaded questions. But so let's address the last one. Should you really only be using this vendor? There's only a few vendors out there, so you're going to rule out all your vendors very quickly if you go that approach. Going back to your first question, I find a lot of times there's just so much data and technology and models that are needed and developed and created to integrate these complex ASICs, whether it's a DDR4 PHY, a PCIe PHY, or some sort of ARM core. It doesn't matter. It's easy to miss things, and I see it all the time, right? An ASIC designer I'm working with, right? We're working on generating some die models for another MCM, another substrate design, and a simple script error in his Tickle script disconnected all the mem caps when he extracted that power domain. So all the mem caps. So we had like 200 nanofarads of on-die capacitance, but when he fixed that little one line, right, that connected those mem caps to the grid, suddenly we went from 200 nanofarads to 1.1 microfarads, which is a more realistic number for this core rail. And so it's a very simple human error, right? These are all script-based die modeling tools, and these things happen. And so this is where you go back to the ASIC designer or the IP vendor and you say, hey, how many mem caps are on this power domain? Okay, so let's just say 100,000, right? Okay, 100,000. Okay, what's the tech file say for the DK that you're using? Okay, it's DK of this. All right. What's the height between the plates? Okay, it's this. All right. What's the area of each mem cap? Okay, got it. Okay, so C equals epsilon A over D, where epsilon is your dk and your E sub r, which is 8.854 times 10 to the e to the minus 12 farads per meter, right? Right. So that whole long number, right? So you take that, you multiply that by the area of the mem cap, divide that by the distance between the plates. You're going to get a value for one mem cap. Multiply that by that 100,000. Now you have a good approximation of the total amount of mem caps on that grid. If that doesn't match what you extracted, usually it's simple things that you just need to work with these vendors. And I've seen this time and time again internally with our ASIC teams and even externally with other IP vendors, where you just need to work with them to address it. And there's a lot of back and forth, and this is kind of part of the design process, in my opinion.
Yeah, so I guess the takeaway from that is they do actually know what they're doing in terms of building the ASIC. It's just
I do.
something gets lost in the translation between
Yep.
the actual physical design and the documentation that they give you so you can do any kind of model.
Yeah, and a great example, one IP vendor for this ASIC that I'm working on, it has a PCIe PHY on there. And so in the documentation, it actually says in the PCIe PHY, right? Because you have PCIe AVDDC, AVDD, and then H, right? You have multiple power domains, okay? It says the C die for each of those power domains needs to be approximately this or greater. And so we're looking at the die model, and they actually documented it in this instance, right? Okay, it needs to be this or greater. And we looked at the die model that we got, we're like, it's not that. It's less than this, it's less than that. And so we went back to like, oh yeah, good catch. That's just an error. Here's the new die models, right? And so that was a big deal because if we were to use those, there's no way it would have passed spec. And so these are just some. It varies from one IP group to another, but you see, in that instance, they documented it, right? So here we could check and say, okay, it's clearly not right. This is how we address it. We asked them. We got the new models. And it goes back to the earlier point. Okay, maybe when they ran their script, whether it's Tickle or whatever die modeling tool they're using, they forgot to turn on a switch and include some things in their extraction. That happens.
It sounds like at the end of it, you managed to get this figured out after plenty of headache and gnashing of teeth and emails back and forth with the PHY vendor just to get them to admit, oh yeah, we made a mistake. Here's the updated model.
Yep, that's correct. And so we even work with them to even loosen the spec, which is great. So
Okay.
um, sometimes these vendors can put things a little tight, and so um, the takeaway is it never hurts to ask, right? And so that goes back to what I was saying before: ask for a quality report, ask, challenge. Just don't blatantly trust a model just because you got it from this vendor, because we're all humans at the end of the day, right? Not everything is running on AI yet, and and being generated by machines. So hopefully, we're doing our due diligence and checking these models, and it helps over design, right? And that's the whole premise here, because there's only so much you can do with what you have, and so you need to really ask to make sure you have the right models.
Yeah, and you mentioned, loosening the spec after I don't want to say complaining, but asking about it. Convincing them to loosen the spec, I guess it forces you to be less conservative
It
with your
does.
design.
It
And I
does.
mean,
Yeah.
that's something I've had to deal with, not necessarily in the context of ASIC design, but having to ask a vendor, hey, do we really need to have, this power level coming into this pin? This is an RF design. And they tell you, well, we're a little more conservative on that than we need to be. And they tell you can actually go as low as this, and we've had it work. And so that's always nice to know what your real limit is versus what they tell you the limit is.
Right. Right. Agreed. Yeah. In this case, this PHY that we were integrating is actually also a DDR5 PHY. And so it's made to run at DDR5 speeds, but the spec they put on you was for DDR5 speeds, which is really not needed for the speed we're running at DDR4, right? And so,
I see.
but sometimes unless you ask, you wouldn't know, right?
Sure, sure. So the other thing that you brought up, which I thought was really interesting, and I know we've been talking about ASIC design here, but you mentioned that working with Steve Sandler to work on a power supply at 2,000 amps.
Yeah.
Now, usually when you hear numbers like power supply at 2,000 amps, you're probably not thinking, oh, this is for a digital system. And I think a lot of people, when they look at digital systems, they say, oh, it's a small device. It's only got some chips on it. It can't be using up that much power. But when you start to look at stuff like data center architecture, I
Mhm.
mean, those power levels are becoming much more common. I actually just saw something recently from Reed Semi on LinkedIn, and they were showing an image of a board that was running at 1,000 amps, and you could see the socket for the processor and
Mhm.
everything on it, and you had all the VRMs all the way around it with all the different phases, and so that's at 1,000 amps. You guys are already at 2,000 amps.
Yeah. So where this came from, right? Steve has a lot of customers that are at 1,000 amps and 1,500 amps. I think he has a couple at 2,000 amps. I'll let him speak to that. But the whole premise is that Cisco, AMD, NVIDIA, Intel, they're all making substrates for ASICs that are pulling 1,000 plus amps. Even Broadcom, right? And so the takeaway here is Steve needed to be ahead of the power curve, right, to support those customers, and he wanted to create a step load to support that next generation of power testing for substrate level, testing, right, for your PDM. And we needed to create a power supply to support that, and so that's where this whole paper kind of came about. And we're excited because how do you even design for 2,000 amps? What are the challenges from a measurement perspective? And so if you think about, we're talking about 2,000 amps for a core rail at sub 1 volt. Okay, so that means we're talking about PDNs in that 30 to 40 micro ohm range, right? So, okay, that's one thing if you're talking about measuring that with two connectors attached to the PDN. But as soon as you use a probe, what I've learned working with Steve and Heidi is your common mode rejection ratio becomes dominant. And you have to have a common mode rejection ratio well over 100 dB. In fact, Steve just proved this and taught me this. Just to get down into that sort of impedance measurement range with a probe, you need to have a CMRR over 100 dB. And
Is
so
is that because the common mode noise just swamps out your receiver?
no, it's because there's common mode rejection ratio basically is how you mitigate the ground loop error, right? And
Okay.
so Steve makes these injectors, right? He makes a diff amp, which is a great. I have both this and the passive one. The diff amp is an active one. It only has a CMRR of I think it's like 60 dB or just under, or right around 60 dB. And then he has a passive injection transformer, which is basically a common mode choke, right? That one has less CMRR than the diff amp. And where you start to see this CMRR error creep in is towards the DC area, right, of frequency range. And you don't see it until you get below so many micro ohms, right? When you run 100 micro ohms, you won't see that CMRR error with the diff amp. But when you run 100 micro ohms and you're using that combo choke, you're going to see it because there's going to be a nice hump in your impedance from DC to a certain frequency. And that's the CMRR error. And the only way to get rid of that hump is you need to go to a device that has a better CMRR, or you're not measuring down on that bandwidth range. And if you think
Okay.
about it from a PDM perspective, we want to be in that bandwidth range because our power supply, where it's impacting the PDN, it's in that DC to like that megahertz range, right? That's right where the PDN of the ERM is really important. We want to see what the control loop's doing. If we want to see what our loop bandwidth is doing before our bulk caps are kicking in, that's right in the sweet spot. And so we really care about the CMRR being really, really high to mitigate that, especially in these low impedance measurement sort of applications.
So at 1,000 or 2,000 amps, I mean, this is peak current or this is average current?
Oh, this would be average current. Yeah.
Average current. That's a lot of current.
Yeah. Pretty
So
crazy, right? Yeah.
yeah, exactly. So you had said, I think you said that Steve was doing substrate design for
Oh,
those.
I won't speak too much of it, but yeah, he's making things that plug into sockets, things on
Okay.
interposers. He's developing custom and semi-custom and off-the-shelf stuff. He's got a whole new bunch of stuff that he's working on. It's very exciting. I won't spoil it, but it's going to be fun to play with these as these get to come out. If I will say for the folks listening, I just ask Picotest if you're interested. Some of these products are really cool. I mean, it all kind of started with his first water cooled probe that he came out with about a year ago now. He actually created the first GaN based water cooled probe, and the reason why it's water cooled is because he needed a better way to do PSNR, PSRR sort of measurements, right? So right now the line injector is limiting your bandwidth, right, in terms of how high of a bandwidth you can measure your PSR, and that's because of the inductance between the injector and the line and your duct. And so what he did is he moved the line injector into the probe head so you can put it right there on your board and remove all that path inductance to increase your overall bandwidth. And so in doing that, not only increase your bandwidth, but you can increase your slew rate. And so um, there's lots of really cool benefits. But because he did that, he also had to think of ways how to manage it. I mean, you have GaN in the head, you're pulling watts, right, in this little area, and we're talking like amps to tens of amps. How do you cool it? So he
Right.
refrigeration sort of solution. So I have one. Um, like the water lines coming out of the probe head and going into this pump, right? And so then you have your signal lines, right, going to your function generator or your VNA, depending on what you're using as your modulator. And then you have your RF coax coming out, going to the other port. So it's very interesting, but it's really cool when you think about what we're going to have to move towards to do these complex sort of measurements as our sensitivity from PSR gets lower, and this is what you have to move towards. And that all kind of manifested, I think, for Steve into these next generation of, more powerful step loads that he's created, because he had to get past this to get to that. So it's really exciting if you're following what Picotest is doing.
To everyone that's been out there listening, we've been talking with Ben Dannon, who works at a major aerospace and defense contractor. He's also going to be speaking at EDICon on October 4th. If you're watching on YouTube, make sure to hit the subscribe button, hit the like button. You'll be able to keep up with all of our tutorials and podcast episodes as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. Thanks, everybody.